All right, so in France, sorry, this is a little small. So as though the price of grapes were fixed throughout the entire country of France, in this example anyway, let's say somewhere in France, grapes are 1.75 euros per kilogram. What is the cost of grapes in dollars per pound? You guys try this one? You guys try this one too? One of the tricky things about this one is that it asks us to do one of these unit conversions, but deal with units that are on both the top and the bottom of a fraction. Whereas a lot of the examples we saw last week were just looking at the tops, kind of how do we convert from the top, we put this other thing on the bottom. So let's go through this, and it'll be good practice for when we go into density, which is what we'll be working on for a while today. So 1.75 euros per kilogram. We have to understand first how to write that as a fraction. So what does a fraction look like that represents 1.75 euros per kilogram? How would you write that? What does it mean when something says per something? Division over. So you put whatever the thing is on top and then per whatever on the bottom. And in this case, when no other number is given, if it says per kilogram, what that really means is per 1 kilogram, right? Or per each kilogram. So we can express this as the fraction 1.75 euros per 1 kilogram. Is that the right symbol for euros?
Yeah.
Is that right? Okay. All right, so now we have euros per kilogram as a fraction, and we have to convert the euros to dollars, and we have to convert the kilograms to pounds. So we have to set up 2 more conversion factors, but we have to worry about which side of the fraction, top or bottom, our unit's going to be on to make sure that they cancel. So what's the rule about getting units to cancel with this method? How do we have to write the units to make sure they cancel properly? What? Diagonally. So if you want to cancel a top unit, you got to put the next one on the, well, sorry, I'll do it at your side. A top unit, you got to put the next one on the bottom. And if you want to cancel a bottom unit, you got to put the next one on the top. So which one do you want to do first? Does it matter? Doesn't matter in this case because multiplication you can move around the orders of whatever, but do you have a preference? Does anybody care? How would you do it?
Euros.
You do euros next? Sure, why not? So our next factor is going to be the one that converts euros to dollars. That means that we want to convert euros, we want to get rid of euros and end up with dollars. So we put the euro on the bottom and we put the dollar on the top. Is that the right symbol for dollars? I think I know that one. All right, and then we don't even have to worry about the numbers yet. We can just, once we get all our units set up properly, then we can go back and fill in the numbers. So this will allow us to cancel euros and end up with dollars. The next step then asks us to go from kilograms to pounds. How are we going to put our units to cancel kilograms and end up with pounds? Which side? What?
Kilograms at the top.
Yeah, in this case, kilograms is going to go on the top. And pounds is going to go on the bottom. So now kilogram cancels over here. Even though they're not right next to each other, we can see that we have a kilogram on the bottom and a kilogram on the top, so those can cancel. And this is a major source of mistakes that I see in these conversion problems, is because we do so many conversions where you always put the thing you want to get rid of on the bottom, it's almost like second nature sometimes. And so people say, oh, I want to get rid of kilograms, I put the kilograms on the bottom. But if the unit starts on the bottom, you actually have to put it on the top to get it to cancel. So think of it as diagonal or top to bottom or something like that. Now we just need to fill in our numbers. So dollars to euros, we're told at this particular time the exchange rate was $1.36 to 1 euro. And then kilograms to pounds, that would be a number that you need to look up, or like this was on an exam or something that I need to tell you. Does anybody know what that number is? Yeah, it's 2.2 pounds per kilogram. But that's not one that you have to have memorized necessarily. Although if you're going into healthcare fields, that's a good one to know, right? Because medicine is often dosed in milligrams per kilogram. So you have to know how many kilograms somebody weighs in order to look at the medication and other things like that. All right, so now all that's left is for us to actually do the calculation. We have canceled our euros, we've canceled our kilograms, so now we have dollars on top, pounds on the bottom, that's dollars per pounds. And if we do that math, that means multiply through everything by the top, divide through everything on the bottom. Does anybody have a calculator handy? Punch that out. What do you get? 1.08, and that will be dollars per 1 pound. So 1.0, of course, dollars we usually put in the front like that, as you know. And another way, while we're thinking about this, let's write a few more ways that that same quantity could be expressed, just in case it comes up later, so you don't get confused. So another way we might write this, and you've probably seen this, 1.08 dollars per pound, where it's just kind of like a diagonal line. Or let's say it was a unit that had words, and we wrote dollars. It seems trivial in this particular example, but sometimes a unit will be given with this kind of slash notation where the fraction of the units is given just kind of in line with the number. It doesn't get its own top and bottom. And so you have to realize that that's the same as writing this thing top to bottom like this and saying 1.08 dollars divided by or per 1 pound. That actually means the same thing. All right, so thanks. I think that was helpful. We'll be doing some more stuff like this when we get into density next. Other ones, other homework problems that got you stuck? Nothing? Everything was good? All right, well, given we're going to miss this class next week for the Labor Day holiday. So sorry, you might have to find something else to do that evening. But we will have lab that week. So we'll have our first quiz on the Wednesday, actually, right before lab. Normally we'd have quizzes on Mondays, but because there's no class on Monday that week, we'll do it right at the beginning of lab. And that will cover this stuff as well as what we go through today, chapters 2 and 3, or 2 and part of 3. And this kind of stuff will definitely be on there, so make sure you're practicing through the homework. All right, so the next thing we're going to look at here 5 minutes is density. What is density? Yeah. It's what? It's mass divided by volume. So that's one way to define it, just based on the mathematical expression. Mass divided by volume. What does it mean? What does the quantity of density tell us? Why is that an important quantity? Why might we need to know mass divided by volume?
For liquids?
Okay. For liquids, yeah, we often use density for liquids, although gases and solids also have density. But yeah, so were you thinking of something specifically? Like where would you see that there was a density of a liquid? Why would that be important? No, nothing in particular? Okay. Can anybody think of a particular instance in which you needed to know the density of something, or that you experienced the density of something? No? That's fine. I don't know if you thought about it or not. Mass divided by volume, that's certainly how we calculate density, but it can also be useful just to come up with some words to describe it or how we think of it, what it actually means. So a definition of density would be the amount of matter or stuff in a given amount of space. So how much space does a certain amount of mass take up, a certain amount of matter? If it takes up a lot of space, then it's very not dense. If it takes up a very small amount of space, then it's very dense. So you can think about it that way. What units do we usually report density in? If it's mass divided by volume, I mean, there are various units for mass, various units for volume. What kind of units do we usually use, you know? Yeah, we usually report mass in grams and volume in milliliters. So our density is often shown as grams per milliliter, or sometimes written as, oops, I'll just skip the grams per centimeter cubed, which is a cubic centimeter or a cc. Those are the same. 1 cubic centimeter is the same as 1 milliliter. So that's how we usually report them. What does anybody know a density of a substance, like an actual number? There's one density that you should know. Water. Anybody know what it is? Yeah, so depending on your units, it's either 1 or 1,000 or something. We usually think of it, well, I think of it just because it's easy, as 1 gram per milliliter or per cubic centimeter. It's actually a little bit more complicated than that. Density changes with temperature. So so you really need the temperature of water, and it's really like 0.99 something, and then at really low temperatures it can change. So anyway, we think of it as just 1. So the density of water is 1 gram per milliliter, which means every milliliter of water weighs exactly 1 gram. Again, ideally, not exactly right, but close enough. And then another way we would write that is just 1 gram per milliliter if we want to use those inline units. This is helpful for a lot of things. One, we can, well, one thing that we do with this is we actually can check our balances and check our different measurements, because we can measure something. Let's say we're not sure if a particular device is calibrated right. In fact, I just did this in my house like a couple weeks ago, and this could be just because I'm a huge nerd, but so one of my kids was sick and had to have the liquid amoxicillin, you know, the like pink stuff, like pink bubblegummy stuff. And so they gave us a little syringe with the amoxicillin, of course. And we had this old like medicine spoon thing that we would use from when like I was little. It's shaped like an alligator and they like that. And so we were like, well, we should check to see if these measurements are actually right, because we don't want to be giving our kids the wrong amount of medicine. So we took it up in the syringe, and we found there was actually a mismatch. And so we were trying to figure out where that was. And actually the alligator was okay, but the syringe, you had to, you know, there's like different parts on the plunger that it could potentially go to depending on the syringe. So we were measuring to the wrong part. But the way we figured that out is we pulled up some water in the syringe and then squirted it onto a scale for balance at home that we use for like coffee and cooking and stuff, and found and did by mass and saw like, oh, okay, well, if I had really pulled up 5 milliliters, it should weigh 5 grams. But it actually weighs 6 grams, so that means that we were looking at the wrong line and we didn't quite do it right. So you can kind of use that equivalence to measure your stuff, and we did it fine, and then of course, it doesn't matter because the kid just like spits half of it out anyway. But we were trying to be really precise. So that's density. So let's look at some different densities of things, and rather than just kind of put up a list, I'm going to grab a picture from the book that I think is kind of nice. Let me pull this up. This is on page page am I on? 45, 46. So what you see here in the little picture is a beaker full of water with 5 different things in it. A cork, ice, water, okay, the water is the liquid, aluminum, and lead. And you'll notice that the different pieces end up in different places in the water. So you can probably see by their densities what that relationship might be. Based on that, based on just looking at those numbers, the density of the cork, ice, water, aluminum, and lead, and then what you see of them in the actual beaker, what can you say about predicting the behavior of materials based on their density? What do those numbers tell you?
Things that are denser than water will sink.
Yeah, right? And things that are less dense than water float, right? And does everybody see that? How the things that are more dense sink and things that are less dense float? And then beyond that, you can also see that the ice is sort of like floating, but just a peaking of the tiny corner of it is like peaking above the water, whereas the cork is like sitting way up on top of the water. So you can see the difference in the density of those also. Ice's density is nearly the same as water, just a little bit less, so only a little bit comes out, whereas the cork is much less dense than water, so most of it is now out of the water. And so this would be true not only with solids, but with liquids as well. And without maybe, well, you can look at these if you want, but if you see like a puddle outside, you know how sometimes you see kind of some rainbowy colors on the top? Anybody know what that's from?
Oil.
Yeah, oil or gas usually that's kind of gotten in there. So is the oil or gas floating on top of the water, or is it sink down below the water? Top. So we would expect oil to be less dense than water, and that's true. They don't have like motor oil here, but olive oil, you can see gasoline, less dense than water. That kind of trips people up sometimes because you think, well, oil is like thick, it seems like thicker, so it seems like it would sink. But if you pour oil in water, you're like, pour oil in a pot of boiling water or something, it kind of makes little droplets and floats in the top because it's actually less dense than water. And so density and viscosity, which is a measure of how thick or how what quickly something flows, those are not really related. They're not really the same thing. So just because something seems thick doesn't necessarily mean that it's dense, that it's heavy. And the oil example is good for that. So you can see some various densities of some things. Water at 4 degrees C is 1.00. And then, stuff made out of water like urine, plasma, and milk is right around 1. And then, super heavy liquid like mercury is very dense. And then you can see the gases, it's not a great comparison because actually gases are reported in density at a different unit. Gases are so much less dense than liquids that these numbers would all be in the thousands. So we make it grams per liter instead of grams per milliliter. We essentially divide all the densities by 1,000. So I think when you have a chart like this, you're trying to compare them. It seems like it would make more sense to keep everything in the same units, but it is true that the gases are usually reported in grams per liter. So I guess that's how the authors decided to do it. Has anybody ever tested the density of anything? Do you know why you might do that? No?
Like bone density.
Sure. So bone density, what might that tell you?
Well, it's like bad to have low bone density.
It's bad to have low bone density. Yeah, because what does that mean? Yeah. So what's happened? What happens? Why are, how do I want to phrase this? What is it about bones that makes some bones less dense than others? What do the less dense bones that you don't want have? Yeah. So what does that cause? Okay, what is that? All right, so it's like, yeah, so somebody said it. So we're kind of going around in circles. Like, what's less dense bones? Well, when you have osteoporosis. Well, what does osteoporosis mean? Well, when you have less dense bones. We just do this all night. But somebody said, like, the porous bone, right? The osteoporosis, it means you have holes in your bones. So now the density of your bones has decreased because air is less dense than solid bone. And if there's air pockets in there, then you now have less dense bone. So that's where that happens. Other times I've kind of pulled the class and asked about density, people have come up with, sometimes in cooking, like if you're making any kind of fermented thing, like beer or wine or something like that, you often measure the density of the starting solution, which has sugar in it. And that tells you how much sugar is in it, so then you can calculate how much alcohol it's going to make and how after the fermentation. They use a different term for it called specific gravity, but they're essentially interchangeable. Specific gravity is the density compared to water. But since water is 1, anything compared to 1 is the same number, so it's essentially the same thing. But you might hear that term specific gravity. It's kind of an older term. The other place that you might see it is if you check the coolant in your car. Anybody ever do that?
Yeah.
Yeah, where you like suck it up in the little bulb thing, and then there's a little ball, and like where the ball goes tells you if your coolant's good or not. That's also a measure of density. Coolant is a mixture of usually antifreeze or ethylene glycol and water. Ethylene glycol is much more dense than water. And so if you have the right ratio, then you have antifreeze capability. If that density gets down close to 1, that means that you've mostly just got some water in there, and that's not going to work. So that means you need to get some more coolant in there, change that coolant up as it breaks down. So that's where you might have seen density, or apparently not. Maybe sometime in the future you'll measure some densities of some things. So let's look at how we use density in these problems. Now the good thing is, density works just like a conversion. It's just like saying there are 2.2 pounds in a kilogram, or there are 100 centimeters in a meter, but we're saying there's a certain number of grams in a milliliter. So it's a way to convert between grams and milliliters. It's just different for every substance. So it's not going to be a constant conversion factor. So let's say that you have, oops. You need to give somebody 2.0 teaspoons of cough syrup. And the density of cough syrup, what would you guess? Would you say that it is more or less dense than water? More? Why more? Because it's the syrup, yeah.
Like the mix and everything that goes with it is more.
Yeah, generally cough syrup is still based on water, right? It's still going to be mostly water. But then it's got all this stuff in it. So if you take something like water and you put a bunch of stuff in it, that's increasing usually the density or the mass of that stuff. So yeah, syrups, anything with a lot of sugar in it, it's going to be more dense than water. So this particular cough syrup in my example here is going to have a density of 1.20 grams per milliliter. And then the question is, what is the mass of the cough syrup? How might you go about determining that? First off, we have to figure out if we have all the information we need, and if not, we need to get the information we don't need. So do we have all the information we need here, or do we need something else? What else do we need? Yeah. Yeah, so if you think about this, sorry, I'm going to keep it a little strong. If you think about this in terms of that roadmap, or like how we're going to convert it from this unit to this unit to this unit to this unit. If we start with teaspoons and we ultimately want grams, because we're given teaspoons and we're asked for the mass, we don't have any factor that gives us teaspoons to grams, but we do have grams to milliliters. So that missing piece is teaspoons to milliliters. So let's write that down as our plan. We're going to go teaspoons to milliliters to grams. For this milliliters to grams step, we can use the density, because the density tells us how many grams are in each milliliter. How do we find teaspoons to milliliters? Yeah, we have to look that one up. Does anybody know how many teaspoons are, or how many milliliters are in a teaspoon? Close. It's 5. 5 milliliters in a teaspoon. So let's put that, let's say we look that up. 5 milliliters. It could be helpful to remember those conversions. So 5 milliliters is 1 teaspoon, 3 teaspoons in a tablespoon, and 2 tablespoons in an ounce. So 5 milliliters is a teaspoon, 15 milliliters is a tablespoon, and 30 milliliters is about an ounce. Like, you don't need to know all those numbers, but they can be helpful if you're cooking or mixing drinks or something. All right, so let's set up our equation now that we've got all the conversions we need. Actually, before I do it, why don't you try to do it? See if you can set up that equation and come up with a conversion, and then we'll see how we did together. You got it? So a couple people are still working, so give me another minute. All right, what kind of numbers you got? You want to throw it out?
For the answer,
Yeah.
12 grams.
12. Yes, no? Other numbers? No numbers? What?
Did you say 12?
Yeah. Is that what you got? Okay, let's see how we do together. So we're going to set it up as 2 teaspoons, and since it's just 1 unit, we can just put that over 1. Then we want how many teaspoons are in how many milliliters, so we can cancel the teaspoons. Then our next one's going to be milliliters to grams. Cancel the milliliters. And so then we're left with grams. So let's fill in those numbers, and we'll be ready to go. 1 milliliter, oops, 5 milliliters in 1 teaspoon. And then we're given the density as 1.20 grams per 1 milliliter. Multiply all that out. 5 times 2 is 10, and then 10 times 1.2 is 12.0. Now, if you just said 12 or not without the 0.0, that's okay. Remember, we said that we weren't going to go through all those rules of properly assigning the how many zeros you need after it. But that should be about 12.0 grams of cough syrup. So does anybody want to admit that you didn't get it right and then show us what you did wrong so that we might learn from that? Nobody will judge you, right? No? Okay. Well, think about that with future problems. Sometimes it can be really helpful because if you made a mistake somewhere, chances are someone else made that mistake too. And if you could be the brave one, you probably help somebody else out as well. All right, let's try one more. And then we'll move on and talk about matter and energy. So let's say we have a glucose solution. You know what that is? It's like a water with glucose mixed in that you might give somebody either intravenously or orally, depending on how they need their glucose. So this particular glucose solution has a density of 1.15 grams per milliliter. How many liters must be given to, I guess we'll say give again, to give 575 grams. So you're given density and you're given a mass. Now the question is, how many liters do we need? Which might be a totally reasonable request, right? You calculate your mass based on a body mass thing, but then the glucose solution itself is a liquid, so you're going to measure it in a volume. And it's a big thing, you need a bunch of it, so you're going to measure it in liters. So how many liters do you need to make sure that 575 grams go in? See if you can set that one up and calculate it, talk with each other, and compare and see how it goes, and then we'll look at it together again. Oops, I didn't save this yet.
I have a question.
Yes?
Are we supposed to write the same method or we can use any method?
You can use any method, yeah. If you've done these kinds of problems before, there's lots of different ways that people like to do them. So whatever works for you, as long as it's coming out right at the end, is fine.
Calculating minutes.
All right, how'd that go? You think? Maybe? Maybe want to shout out some numbers and feel good about it? What? 0.5? Anything else? All right, let's go through it, take a look. So we're gonna start again with that 5.75 grams. One thing I saw as I was looking at your papers, which I do just because then I can address things. Some people, it seemed like we're struggling of deciding what number you start with. Do you start with that density number, or do you start with that 575 number? How did you make that decision? Which number should you start with and why? Nobody? Okay, so, well, I think that is always an issue. With these types of problems, they always give you a couple sentences and you have to kind of, that's a lot of the trouble, a lot of the difficulty of these problems sometimes is just picking out which numbers are important, which ones you need to start with, how you set up that plan.
Would you start with the 1.15 because it gives you like a top and a bottom, like grams per?
Okay, so maybe the 1.15 because it gives you that top and the bottom, kind of like.
Gives you something to like cancel out.
It's okay, so there's some more stuff to cancel out. That's a possibility. In this case, the tricky thing about this one is you can't, I mean, multiplication is what they call commutative, which means it doesn't matter what order you do it in. But if you start with the density, you actually have to start with it upside down, or it's not going to work. So let me show you why that is and how we can actually decide how we're going to start. For me, the trick to it, or the idea behind it, is setting up this plan. So rather than just kind of writing things down, think about the path that you're going to take from unit to unit to unit. We're going to start with this kind of unit, then we go to this kind of unit, then we go to this kind of unit. Let's see how that works down here. In fact, it might be helpful to look at the end. The question in the end asks us for what? What kind of a unit do we want to end up with? Liters. So the liter is going to be the end of our plan. And we don't know how many steps we're going to take here. But what are we going to start with? Just seeing that liters there can kind of help you look at this, because can you take grams per milliliter and then just get liters? You can't really, because there's like 2 units there. So you'd have to kind of make one disappear or something. And I'll show you how we could do that, but it's not really clear how we could do that. If we start with grams, we're starting with 1 unit, then going to something else, then going to something else. And that seems like it works a little bit better. So if we start with grams, we can't go directly to liters because we don't have that unit. What relationship do we have?
Grams to milliliters.
Yeah, we have grams to milliliters. So we can go grams and then to milliliters and then to liters. And that's our path that we take. So if we do that, that's going to be 575 grams. And then see that here is where this upside down density comes in. If we just wrote down that density, we'd be flipped wrong. And so you'd end up with liters on the bottom when really we want the liters to be on the top to be our regular number. And then our next conversion is going to be milliliters to liters. And now we just fill in our numbers. Remember that density is a certain number of grams per 1 milliliter. Multiply through all the tops, divide all the bottoms, and this comes up out to 0.5 milliliters, or 0.5 liters. So half a liter would be 575 grams. Okay, sound good, maybe? Keep practicing these like anything else. This is not magic. This is not something that some people can do in their brains and other people can't do in their brains. This is a skill that you have to practice and reinforce. And once you do it a bunch of times, then you'll be able to get it all the time. So go to the homework, practice these problems, and I think you'll be in good shape. Yeah.
I have a question.
Yeah.
I got that same answer, but the other way where I didn't switch the 1.15 number.
Mm-hmm.
So I'm wondering if it's a fluke for this specific situation, or if I will always, if it's like.
Probably not. How did you, can I see your? Oh, no, you're fine because you ended up with the grams on the bottom at the end. So then it will still work.
So will work every time.
Yeah, so let me actually put that up there. So, like I said, multiplication can go in any order. So it doesn't totally matter what you do first, but you have to make sure to be consistent all the way through. So, Jessica? All right, good. I'm getting closer. I'll get them all eventually. Did it like this, starting with the density, and then you still have to track those units. So I think this method's a little bit harder for me to think about because I think, well, what do I go from grams to? What do I go from milliliters into? In this case, we need to go from, we need to cancel out the grams and also the milliliters. So we need to get, whoops, sorry. We need to get rid of milliliters and have liters. Wait, did I do something wrong here? Let me see your thing again.
That's what I did. And
what you
then I
did?
converted it to 1,000 milligrams over 1 liter, or milliliters to 1 liter.
So you went
Cancel out the milliliters first,
1,000 milliliters
because that was the measurement I knew.
per 1 liter, like
And then I
that?
multiplied it, and then I knew I needed to divide out the 575. So I got rid of the grams.
Oh, so the grams cancel like this, the milliliters cancel like this.
And then I knew. when I
That shouldn't have
multiplied it, it was
calculated to the right.
1 over.
Oh, so then you did the
Then-
inverse of it?
Yeah,
Okay, so here's where this comes up. What does this number come out to, do you know?
it was 1 over 2, because there's no unit on the top.
Yeah, so you'd end up with this weird quantity of 1 over 2 liters, where there's no unit on the top because all the top units have canceled, and the number on the bottom is liters. But that's not really an answer because that's not liters, that's 1 over liters. So then you have to put 1 over that whole thing to flip it back around forwards. But it works, right?
I got the right number. I don't know if it'll always work.
Wait,
I just divided 1 divided by 2.
that, this would actually be 2, right? This comes out to 2 divided by liters. So 2 nothings divided by liters, and then you have to take 1 divided by that whole thing, and you get 1/2 of liters. Don't worry about it. So the answer is yes, it works if you do it that way, but it gets a little bit more confusing. So nice job thinking that through and like getting it, because it does absolutely work. But I think a lot of us are confused, so we'll probably stick to the other method. But honestly, if that works for you and you think about it that way and you can flip it around in your head, then great. Just, yeah, it works. Thanks. All right, should we move on? Or you want to talk about that some more? Just forget that last part if you're confused right now. Okay. Let's talk about matter. What's matter? Yeah. Sure.
With all the conversion tables, is there one set conversion table, or you just remember all those different ones? So that you're looking into one.
You don't have to remember anything. You have to remember the three that we talked about last week. Centimeters, or centa whatevers, kilo whatevers, and milli whatevers. Any other numbers you'd be given.
Okay.
So, densities or gallons and ounces or whatever else we've been doing stuff with, pounds, those numbers would always be given to you. So you need to know, you need to be able to do the centi, milli, and kilo whatevers. Other than that, you'd be given the numbers. Yeah.
So do we have to worry about anything bigger or smaller than that, like
Nope.
tera, whatever?
Well, yes, but I would give you the numbers. So
Oh,
same thing.
okay.
You don't have to remember what those quantities are. All right, so what's matter? Thank you for asking that, by the way. What? Yeah, anything that has mass takes up space, and it takes up space. That's matter. So the reason I kind of put this in the middle, we're going to make a little, not quite a flow chart, but like a tree of the ways that we can divide up matter. And first it seems kind of simple, and then it'll get a little bit more specific. We're going to end up with 4 different categories at the bottom. So from matter, we're going to put matter into 2 different categories. One of them is the pure substances. What do you think the other one is? Actually, compounds are considered pure substances.
Mixtures.
Mixtures, yeah. So we've got the pure substances and we've got the mixtures. We're going to further divide these into pure substances can be either elements or compounds. And mixtures can be either heterogeneous or heterogeneous or homogeneous or homogeneous. So those are our 4 categories of matter. I'm going to give you some examples of each and some definitions of each. And then the point of this whole thing is that ultimately you'll be able to categorize whatever into one of these categories. And it's not always clear cut. Some things can fit into different categories depending on how you're looking at it, depending on your frame of reference, if you're looking really closely or from far away. So they're not always super neat categories, but we will think through it and kind of decide how we want to put things or how we want to categorize things. So starting, I guess they get kind of like more concrete to less concrete going left to right. So we'll start way over on the left. What are elements? It's not like air, fire, water. What? Yeah, like things that are up on the periodic table, silver, gold, carbon, oxygen, those sorts of things. The definition of that is that elements are only made up of one type of atom. So if you have a sample of gold and it's pure, every atom inside that sample is a gold atom. If you have a sample of oxygen, every atom inside that sample of oxygen is an oxygen atom. So there's only one type of atom inside a sample of a particular element. How do you think a compound differs then? Yeah. Two or more types of atoms. And here's kind of an important last part, that these atoms must be chemically bound. Now we'll get into a little what it means for atoms to be chemically bound to one another later. We'll talk about what a chemical bond is and all of that. But the reason that that's important is that really separates these compounds from mixtures, and that's why compounds end up in the pure substances category, even though they have different types of atoms in them. Example of that would be something like sugar. Anybody know what atoms sugar is made up of? Maybe one of them? You can guess. What do you think is in sugar? There's 3 different types of atoms in a sugar molecule. Yeah, carbon, hydrogen, and oxygen. You know anything else that's made of those 3 things? Like everything, basically. I mean, all kinds of, fats in our body, all the other sugars in our body, polysaccharides, starches. We'll talk about a lot of these kinds of things. Things that seem completely not like each other. Right? Gasoline is carbon and hydrogen. Diesel is carbon, hydrogen, and oxygen. So it's like, clearly these are different things, but they're still made out of the same kind of elements. And so those are pure substances, but they are different substances because they have different amounts of those atoms, and they're chemically bound in different ways. So the kind of corollary to this then is that compounds can only be separated by chemical means or chemical reactions. So that means that when you separate the atoms in a compound, you totally change what this thing is. If you take water is a compound. Anybody know what atoms it's made out of? Hydrogen and oxygen. If you separate those atoms from water, you have something that is not anything like water. You have either hydrogen gas or oxygen or hydroxide or some other thing, but it's not like water at all. So you've fundamentally changed the thing, and that's why it falls into a compound. That's why it's a pure substance, because when you do that chemical reaction, you really turn it into something else. Other examples of compounds: water, something like NaCl. What is that? Sodium chloride or salt. Yeah. Again, you separate these things out, you have something that's totally different. So that's the pure substances. We should add some of these examples over here. So like carbon, gold. Has anybody heard of 24 karat gold versus like 14 karat or something like that? You heard that classification scheme? If you go buy some gold, it'll be in different amounts. The 24 karat means pure gold. So that's actually all made up of gold atoms. The lower numbers mean that there's other stuff in there too. Does anybody know why you might want not pure gold? Why you might want like 14 or 10 karat gold instead of 24?
It's cheaper.
It's cheaper, sure, yeah, because gold's really expensive. But there's actually another good reason too. What? There could be a weight consideration, although if you're worried about the weight of something in gold, you're probably not worried about the money part of it either. Like this gold ring is so enormous that it's like hard to wear on my hand. But there's actually like the structural properties of it. So jewelry, you'll often not see 24 karat gold in things like rings or chains or that kind of thing because it's much weaker. Gold is a very soft metal and you can actually bend it and kind of dent it pretty easily. So if you have pure gold, it's going to deform very easily. And if you spend a buttload of money on some fancy 24 karat gold ring, you don't want to be able to just like squish it with your fingers. Right? So that's why they'll usually use that lower carat of gold, which has other stuff in it that strengthens it and makes it a little bit more durable. So let's look at the mixtures. Has anybody ever heard these words for mixtures, a homogeneous mixture versus a heterogeneous mixture? How would you describe them, or one or the other?
A heater and gun. This might
Yeah.
be two different mixtures.
Might be like different things in there.
Mhm.
Yep, and the other ones.
Homogeneous, the same.
Yeah. So what do you mean by different and the same? Anybody? So something about this means you either have different things or you have the same things. You may know what that refers to. What?
Like oil and water.
Like oil and water. That's a good example. What's different about that?
And then water.
So yeah, so
It
you can
doesn't really mix together.
right. So you can clearly see the two domains. Like there's oil over here and there's water over here, and that is really the as you both said, that is the key of this is that homogeneous mixtures we should clarify that. Visibly the same throughout, and a heterogeneous mixture has a not uniform composition, or it's not visibly the same throughout. Visibly not the same throughout. So a homogeneous mixture is something where you look at it, it all looks like the same thing. It's been mixed well enough that it all looks like the same thing. So these are kind of nice to look at some examples. Coffee. Has anybody ever had coffee? It's like blackish, kind of brown. Sometimes you put milk in it. But what's in coffee? What kinds of compounds or substances are inside coffee? What?
Water.
Water. Certainly, most of it is water. What else? Caffeine. What else? Is that it? Sugar. If you put sugar in it, sure, yeah. And then like thousands of other flavor compounds and stuff like that, right? All kinds of whatever makes coffee taste like coffee. So that's an example of a mixture because it has all these different molecules inside it. It's made up, definitely made up of lots of different kinds of things. But when you look at coffee, you can't say, well, the water's over here and the caffeine's over here and the flavor's down here. It all looks the same throughout. So that's what we would call a homogeneous mixture. Heterogeneous mixture, I'll use your example. If you put oil and water together, the oil will settle on top of the water, and you can clearly say, okay, the oil's up here and the water's down here. Of course, if you shake it really hard, then you can potentially form a homogeneous mixture of oil and water. You know what I'm talking about? Like if you have a vinaigrette salad dressing or something, you shake it up really hard, and suddenly you don't see those anymore. But sometimes if you let it sit, they'll settle back out again, and then it's a heterogeneous mixture again. Even like stuff that you don't really think of as classifying in this way, like a sandwich. You guys know sandwiches, like bread with stuff in the middle of it? Same thing, that would be a heterogeneous mixture because you can see the bread and you can see the stuff, and it's not all the same thing. So what are some more mixtures? What are some more homogeneous mixtures?
Milk.
Milk, yeah. In fact, you may have heard this term in relation to milk before. Have you ever seen that, like if you look at the label of milk, it says homogenized milk? That's sort of what that means. It's been turned into a homogeneous mixture. Why would it not be a homogeneous mixture to start with?
Because isn't it just kind of like water and fat?
Yeah, it's just water and fat, well, and like sugar and other stuff, protein, stuff like that. But if you've ever gotten milk out of a cow, which is one of the animals that milk comes from, it like, has anybody ever seen like fresh raw milk? It separates, like all the fat goes to the top because it's less dense. And then there's a water, so there's 2 different parts. And so to make that a homogeneous drink, you have to shake it up. And what happens in like the milk we get at the grocery store is that's done as part of the process. It's just like mixed up really, really hard so that the particles are broken up so small that they're held in suspension with each other and they don't settle back out. So this is where it kind of gets a little fuzzy. Milk could really go in either category depending on your experience of that milk. Is this grocery store homogenized milk, or is this fresh from the cow or goat or whatever raw milk? It's going to be different. What else?
Air.
Air? Where does that fit? Which side? Homogeneous? Yeah. What's in air? Oxygen, nitrogen, carbon dioxide, various other things. And you certainly can't see that, well, even if you could see the air, we wouldn't say, well, the oxygen's over here and the nitrogen's over here. It would all be mixed together. What about over on the heterogeneous side? What would be some other examples there?
Pancakes, you mix them.
I'm sort of like ice cream or?
Like oatmeal pancakes or.
Okay. Or what?
Raisin pancakes.
Okay. Oatmeal. And I guess we'll say raisin pancakes. I think the distinction, or oatmeal raisin together, yeah. The distinction of having like oatmeal or raisin there is actually important because if we just said pancakes, that actually might fit better over in the homogeneous side because the pancake kind of looks the same all throughout. It's got a lot of stuff in it. It's made out of a lot of different kinds of atoms, but it's visibly the same. So with oatmeal pancakes, you can see the little oats in it, depending on how much you grind your oats or whatever for it. And with raisin pancakes, you can certainly see the raisins in them. Any non-pancake based ones that you can think of?
Pumpkin orange juice.
Like what?
Like the pumpkin orange juice.
Yeah, orange juice is another kind of tricky example because it could kind of go either way depending on what your experience with orange juice, right? So we might put them in both categories. Let's say we'll put orange juice in heterogeneous if it's with the pulp. And we'll put orange juice in homogeneous without the pulp. That's a pretty good list, I think. All right, I'm going to throw out a couple things, and let's see where you would categorize them. Gasoline. Who says gasoline is an element? Compound? Heterogeneous mixture? Homogeneous mixture? All right, so a little bit across the board, but it seemed majority was homogeneous. Why homogeneous mixture, those of you who picked that one?
Because it looks the same?
It looks the same throughout, but also the mixture part means it must have different kinds of things in it. What kind of things are in gasoline?
Ethanol.
There we go. Yeah, there's usually a little bit of ethanol in there as an additive. What's the major component of gasoline? Do we know? What?
Petroleum.
It comes from petroleum, yeah. But the one compound that is the major component of gasoline is called octane. Octane is an organic molecule made of carbon and hydrogen. You know, like the octane number on the. What? Yeah, that number, it's like 87 or 89 or 90, whatever you need to have. That's a percentage of octane. So if you're using the regular 87% octane gas, that means that you got 13% other stuff in there, like ethanol, other types of things. There's like detergents that help kind of clean out your engine. There's stabilizers that stop the gasoline from decomposing into other stuff. So yeah, I think that would fit well in homogeneous mixtures. Now, depending on the gasoline, if you had 100 octane gasoline, that would actually go where? Not quite, because octane is a molecule made from carbon and hydrogen. So we've got different kinds of elements in octane, so we would actually put that in compounds. All right, what about ice? Where would ice fit?
Element?
Element? Compound? Why element?
It's just water.
It's just water. Which element is water made out of? So it's more than one kind of atom, right? So we go in compounds, yeah. But you can see how this can get tricky. It seems pretty simple. There's just these 4 categories. You just think of the thing you put in the category. But sometimes we get turned around because we think of things as fitting into certain categories that they might not actually be in when we really consider the chemistry behind it. So take a minute to think about those definitions, and then categorize as you will. All right, let's stop there. Take about 15-minute break, and then we'll come back and talk about energy.